Well, you knew sometime eventually we would make it to calculations. So we got to pull out our calculators and do a little work here. So we're going to talk a little bit about concentrations of solutions, and believe it or not, we're going to talk about stoichiometry again. The principal unit of concentration that we will use is something called molarity, and molarity is generally abbreviated with a big M, and that big M stands for moles of solute per liters of solution. Sometimes we also, rather than writing a big M, we'll write moles over liters. So moles over liters or big M mean the same thing. So I have a problem here. Let's just jump right in. I've got 1.5 grams of copper sulfate, pentahydrate, and I'm dissolving it in enough water to prepare 200 milliliters of solution. So I need to calculate the concentration of this solution in moles per liter. So I've got grams of that copper sulfate pentahydrate, so I need to turn that into moles. So that's what I did here first. So 1.5 grams, and the molar mass that I calculated was 249.69 grams per mole. So I got that number of moles, and when I plug this into the molarity equation, I put my moles on top. By now I was hoping that most people would be able to nearly convert milliliters to liters in their head. So if I took that 200 and divide by 1,000, I get a liter, liters, so I got 0.2 liters. So if I take my moles divided by my liters, I get 0.0300 moles per liter of copper sulfate, or 0.0300 molarity copper sulfate. Notice that I left the water off. I could have included it, but those waters, when that dissolved into solution, just kind of drifted off and kind of became lost in the larger quantity of water that was what we used as the solvent. Okay, molarity allows us to relate moles to liters. So I might want to know how many moles of copper sulfate are in 50 milliliters of 0.3 moles per liter solution. So even though M, the big M, looks like a simple unit, it isn't a simple unit. That stands for moles over liters. So that's a conversion factor. The milliliters would be where I would start. That's the simplest unit. So again, I started by converting it first into liters. I got 0.0500 liters. And then since I wanted to get rid of liters, I put them on the bottom of the next cell, and then the 0.03 moles on the top. So if I multiply that through, I get 0.0015 moles per liter. And I guess I should, in looking at this, I should have had 0.00150. So it should have 3 sig figs. I must have gotten sloppy or tired while I was typing there. Okay, I jumped right ahead, but let's go with it here. I had 0.3 molar copper sulfate, or 0.03 molar solution of copper sulfate, and I want to know how much of that would be needed to contain 1 mole. So if I have 1 mole, that's my simplest unit, and again, my 0.03 moles per liter, the big M, is a conversion factor. So I want my moles on the bottom and 1 liter on the top. So it tells me the moles per 1 liter. So when I multiply this through, I find that this would have 33.3 liters. So it would take 33.3 liters of this 0.03 molar solution to contain 1 whole mole of copper sulfate. Another way of looking at this is if I have, to put this in a stoichiometry type of perspective, if I have liters on top, moles per liter on the bottom, and then moles on the third row, I can multiply down. So you can see that's what we did there in that first problem. We multiplied down. Likewise, I'm dividing up. And this is opposite of what we did when we were using gram stoichiometry. So we started with grams at the top, and then we divided down and then multiplied up. So you have to be kind of careful, keep your wits about you. Just look at the units. I can see that liters times moles per liter gives me moles. And if I have liters, if I divide by moles per liter, I get moles. Actually, if I have moles, rather, and then divide by moles per liter, I get liters. Okay, so let's do a stoichiometry problem. They're not, too intimidating here. I've kind of got the labels on the right-hand side. I've got liters in the top row, moles per liter in the second row, moles in the third row, and then, as always, the coefficient and magic number in the next two rows. So I've got 0.25 mole per liter sodium chloride solution, and it's reacting completely with a 10 milliliter amount of the 0.3 molar lead nitrate solution. So I'm going to start out by putting those numbers on the table. So I converted the volume of the lead nitrate solution into liters. Took the 10 divided by 1,000 to get 0.01 liters. So if I multiply down, I'm going to get moles. So I get 0.003 moles. The coefficient there is just 1, and I filled in all the rest of the coefficients here as well. So if I keep on multiplying, or I guess at that point I'm dividing. Careful. I'll have to fix that slide, but you divide in that next step. So you're always dividing by the coefficient once you have moles. So then I would have to transfer that number over. I'm going to be careful here because I have to multiply, and I did that just kind of subconsciously here. So in that first step, just like we'd done with the dry stoichiometry, I got that magic number. I want moles, so I'm going to have to divide to get units tacked back on that number. So 2 moles times the 0.003 gives me the 0.006 moles. And then at this point, I'm going to take my 0.006 moles and divide it by 0.25 moles per liter to get my liters of solution. And what I got was 0.024 liters of that sodium chloride solution. If you wanted it in milliliters, you could multiply it by 1,000, and that would be 24 milliliters of that sodium chloride solution is what I would need. Sometimes you're aware that these problems have a follow-up question. So let's take a look at a follow-up. Okay, so here's my follow-up. What mass of lead chloride could I prepare? So I'm looking at a product here, and that product's a solid, so we're back to the gram stoichiometry. So I've got to change my labels to grams, grams per mole, moles, coefficients, and then the magic number there. So I'm going to transfer my magic number over to the bottom of that column, and then I'm multiplying up as usual. So to get units attached back on, I multiply by moles. I've got grams per mole there, so moles times grams per mole gives me grams. So if I multiply that through, I should get grams, and it looks like I should end up with 0.834 grams. That's my calculated amount, or sometimes what they call the theoretical amount of the product that I could end up with. Okay, sometimes you have a solution that is more concentrated than what you want to work with, so you have to do a dilution procedure. So I'm going to cut to the chase here and give us the equation M1V1 is equal to M2V2. So one of the first things you want to do is to tabulate your data. So I'm starting out with 25 milliliters of a 2.46 moles per liter solution. So that's my M1 and V1 there. And then I've got a V2. I'm changing this to 500 milliliters of solution. So I'm taking that 25 milliliters and adding water to it. So there's my tabulated data, and I just plug that into the equation, and I want to get M2 all by itself, so I'm going to divide by 500 milliliters. And when I do that, I got a molarity of 0.123 moles per liter, or molarity. You can always check yourself when you dilute something, it becomes less concentrated. So this 0.123 is much less concentrated than the 2.46 that I started out with. So I feel fairly confident that I have a good answer. At least it's in the right direction. In fact, I know it's the right answer. Okay, so what volume of that 2.46 molar solution is needed to prepare 200 milliliters of a 0.1 molar solution? So I know my M1. I don't know how much the volume 1 is, but I know what M2 and V2 are. So I'm going to tabulate everything, plug it in. I want to isolate the variable that I'm interested in. In this case, it's V2. So if I divide both sides by 2.46, things cancel out, and I end up with 8.13 milliliters. So if I wanted to actually prepare the solution, I would take 8.13 milliliters of my 2.46 mole per liter sodium chloride solution, Put it in a container and add enough water to prepare 200 milliliters.